this week. Okay, the tutorial for this week, we will have 3 problems. Any specific question regarding to the concepts for the last week or these problems? Any question? Okay. The first problem, in an experimental test, which is run to determine the kinetic coefficient of friction between a block and a surface. The block is attached to a spring and displaced 150 millimeter from equilibrium. It is observed that the period of motion is 0.5 seconds and that the amplitude decreases by 10 millimeter on successive cycles. Determine the coefficient of friction and how many cycles of motion the block executes before motion ceases. So in this problem, we can easily find the period because, the frequency, because we have the period. According to the problem description here, the period of motion is 0.5 seconds. So easily we can find the natural frequency of the system because in a system with column damping, the natural frequency of the system will be remain the same. So omega n easily can be obtained from the period of the motion because the natural frequency is the frequency of the motion. So it's equal to 2 pi divided by period, which is 0.5, and this is the natural frequency of your system in radian per second. The next step, we need to obtain the coefficient of friction because we did this experimental test to obtain the coefficient of friction between the block and the surface. So we know that in each cycle, the amplitude decreases by 10 millimeter. So 4 mu times by g divided 4 mu times by mg divided by k is equal to 10 millimeter. We know that k is equal to m omega n squared. You know that omega n is equal to a square root of k divided by m. So from here we can conclude that k is equal to m times by omega n squared. And we can substitute, instead of k here, we can substitute m omega n squared. These m's will be cancelled out. So the decrease in the amplitude is equal to 4 times by mu times by g divided by omega n squared. G is 9.8, omega n is 4p, calculated here. And easily we can calculate mu because we know that the decrease in amplitude is 10 millimeter. So of course we need to convert it into meter. 10 to the or 0.01 is equal to this term, and only we will have one unknown, which is mu. We can solve this equation for mu and obtain that the coefficient of friction is 0.04. So this is the first part. So we obtained the coefficient of friction, the first part of the problem. And the second part, we need to obtain the how many cycles of motion the block executes before motion ceases. So we need to obtain the R in this equation. We know that x naught minus R times by 2 mu n divided by k must be less than mu n by k. From this equation, we can obtain R, which is the number of the cycles, of course, number of the half cycles. So we have mu, we have n, k, we can substitute and solve this equation for R, and we can obtain that R must be more than 29.5. We can round this number and it will be 30. So 30 number of half cycles we will have, and the complete cycles will be R divided by 2, because this is the number of half cycles. So the number of the complete cycles will be R divided by 2, or 15. Okay, any question? Is it clear? Okay. The next problem, a mass of 20 kilogram is suspended from a spring of stiffness 10,000 Newton per meter. The vertical motion of the mass is subject to column friction of magnitude 50 Newton. If the spring is initially displaced downward by 5 centimeter from its static equilibrium position, determine part A, the number of half cycles elapsed before the mass comes to rest, and part B, the time elapsed before the mass comes to rest, and part C, the final extension of the spring. So we need to obtain again the number of the half cycles, or R. For this purpose, we can substitute again in this equation for R. We have the initial displacement. Also, we have mu. Of course, mu times by n, which is the force of the friction, is 50 Newton. We have the stiffness of the spring. And finally, we can solve this equation for R, and we can conclude that R must be more than 4.5. And again, we should round it, and R will be 5, the number of the half cycles. And we can obtain the period by using the given data. We have the omega n, which is equal to square root of k divided by m, and the period of the motion will be 0.3. So to obtain the time elapsed before mass comes to the rest, it will be equal to the period times by the number of the cycles. We will have 5 half cycles, so the number of the complete cycles is 2.5. So the required time is 2.5 times by 0.3, and it's equal to 7.5 seconds. And finally, to find the final position of the particle, we know that it will have 5 complete half cycles, and in each half cycles the amplitude will be decreased by 2 times by mu n divided by k. The initial position is 5 centimeter, or 0.05. So we will have 5 half cycles. So by calculating the final amplitude in the last half cycles, you can see that it will be 0. It means that the mass will be located on the initial position, or on the equilibrium position when x is equal to 0. Okay, you can see these are very simple examples for the column damping motion. Is it clear? Any question? Okay. And the last one, we have a system with his surge damping. The experimentally observed force deflection curve for a composite structure is shown. Find the hysteresis damping constant, the logarithmic decrement, and the equivalent viscous damping ratio corresponding to this curve. So in this case, we need to calculate the energy dissipated for each cycle. And you know that the energy dissipated is equal to the area enclosed, the surface enclosed by this curve. So we need to calculate the area enclosed in this curve. We can count the number of the squares located in this area, which is approximately 34, I think. And the dimension of each square, for each square, this length is 1 millimeter, and the vertical edge is 100 Newton. So the area for each square is 0.1 multiplied by the number of the squares, which is 34. So the energy dissipated, the total energy is 3.4. And we know in a hysteresis system with hysteresis damping, it must be equal to pi beta k x squared. So from this equation, we can obtain the beta, but before that, we need to obtain the k, the stiffness of the system, which is the slope of the curve. Again, here, if you look at to this system, the slope of this curve can be obtained from the 2 points of this curve. For example, here you can find the slope of, sorry, here, the slope of this line. We can find the position of these 2 points. One of them is 0 and 0, and the other one, this point, for example, is about 4 millimeter. The horizontal position is 4 millimeter, and the vertical position is about 700. So you can find the slope of this line by using the data of these 2 points, and it's about 700 divided by 4.3 millimeter or 4 millimeter. Okay, so it's an approximation, and this is the stiffness of the system. And now you can calculate the beta from the first equation. From here you can find the beta, because we have pi is 3.14, we have k, and also we have the amplitude of the response. And then we can easily calculate the beta from this equation. Okay, so this is the beta. When we have the beta, you can easily find the logarithmic decrement, which is pi times by beta. And also you can find the equivalent damping ratio, which is beta divided by 2. So these are the characteristics for the hysteresis damping system. Okay, any question? The amplitude is clear here, the amplitude of the motion, because this is the deflection. Yeah, the horizontal axis is deflection, and here it's about this point. This is the amplitude, it's about 4.3 millimeter. It's okay. No other question? If you don't have any question, we can wrap up this session. Yes, no problem. Because as I told you, in fact, when you calculate the area, in this is only an approximation. So maybe the for example, here we consider, let me show you. For example, you can consider this area, this three small parts with these two small parts consider as one complete square, or it can, you can consider, for example, half as half a square. So it's up to you. It's only an approximation. So maybe you count, instead of 34, you count, for example, 33 or 35. No problem. The final results will be approximately the same. If you calculate, for example, for 33, you will see that the response is almost the same. Because in fact, when you deal with a hysteresis damping system, you are finding an equivalent, an approximation or an estimation for your system, and you are estimating the damping and estimating the stiffness in your system. You cannot find an exact value because it's not a spring and mass system. Okay, so only we are calculating the estimation for our system. Any other question? Yes. For part B, in question 2, the time elapsed before the mass comes to rest. For this purpose, you, in part A, you calculated the number of the half cycles. We know that before that the mass comes to rest, we will have 5 half cycles here. We calculated that the number of the half cycles is 5. So once you calculate the period of the motion, you can calculate the times before that the mass comes to the rest. The period is 2 pi divided by omega n, and omega n is square root of k divided by m. So the period of the motion is 0.3. So we know that each complete cycle will get 0.3 seconds. Okay, this is the period of the motion, and we know that the number of the cycles is r divided by 2, which is 2.5. So it will be 2.5 complete cycle multiplied by the time required for each complete cycle, which is 0.3, and it's equal to 7.5. Oh yes, maybe I made a mistake. Yeah, thank you. Yeah, it will be 0.75. It's not correct. Okay, thank you. Any other question? Yes, the shortest will be online. I think it will have 3 different parts. One is the true and false questions, one is the multiple choice questions, and the other one is the essay question. In week 7, which day exactly you want? Yes, we can. So we can discuss this in our Viber group. If all of the students are agreed, we can move it to the week 7 on Thursday, no problem. To me, it's okay. Thank you. Any other question? Okay, thank you for your attention and have a good weekend. Tomorrow I will upload all of the videos on Moodle. You can go through to the videos and let me know if you have any questions. Okay, thank you and have a good weekend. Bye.